All right, well, let's begin. I'm very pleased to introduce our next speaker, Dylan Allegretti, who will be talking about harmonic maps and cluster coordinates. And before Dylan gets started, Dylan won't be looking at the chat, so if you have things you want to ask each other in the chat, please go ahead. And if there's something that needs to be asked to Dylan, I'll go ahead and ask that. So please go ahead, Dylan.
Okay, well, thank you very much. And let me, of course, thank the organizers for inviting me to give this talk. So I'm going to be speaking about connection between harmonic maps and cluster coordinates. And I'd like to begin by just giving a very basic overview of Teichm&uuml theory. On my slides, oh, there we go. So in this talk, when I talk about a hyperbolic metric on a surface, I will always mean a complete finite area Riemannian metric on the surface with constant curvature -1. And so how do you give examples of such things? So one way is as follows. So we could suppose that our surface C is a compact Riemann surface of genus bigger than 1. And in that case, you have the uniformization theorem telling you that the universal cover of that surface is identified with the upper half plane. And there's a very canonical metric that you can write down on the upper half plane. It's this Poincaré metric that I've written here. And that descends to give a metric on the original surface. So that's how you can construct a hyperbolic metric on any surface of genus bigger than 1. And a surface equipped with a hyperbolic metric will be called a hyperbolic surface. So those are some of the basic definitions that will be used in this talk. And so we would like to consider hyperbolic metrics. We would like to consider different hyperbolic metrics on the same surface. And therefore, we're going to do, if we're given a hyperbolic surface, then we're going to define a marking of that surface by some auxiliary surface, which I'll call S, to be a diffeomorphism between the two surfaces. Okay, that's a marking, and then the pair consisting of a hyperbolic surface and a marking will be called a marked hyperbolic surface. And there is an equivalence relation that we can define on these pairs. So two marked hyperbolic surfaces are called equivalent if there is an isometry between the hyperbolic surfaces that makes this diagram commute up to homotopy. Okay, so that is defining an equivalence relation. And then we have the following definition. So let's let S be some closed oriented surface. And then we define the Teichm&uuml space of S to be the space of all marked hyperbolic surfaces up to equivalence. Okay, and perhaps you know other ways of defining the Teichm&uuml space, but this is the one that will be most relevant for this talk. So we're going to consider Teichm&uuml space as parametrizing different hyperbolic metrics on a surface. And there's a basic theorem of Teichm&uuml theory that says if your surface S has genus bigger than 1, then the Teichm&uuml space is homeomorphic to a Euclidean space of dimension 6G minus 6. Okay, so that was all of the stuff about Teichm&uuml space that I wanted to review. And now I'd like to pose a question, which is, what is a good representative for a point in Teichm&uuml space? So I have defined the Teichm&uuml space as a space of these pairs, C, comma, psi. And what I'm asking now is there some way to choose a representative for the equivalence class of pairs, which is somehow preferred? And that will lead us naturally to the subject of harmonic maps, which I mentioned in the title. So this is a notion that can be defined for any pair of Riemannian manifolds, but in this talk, I'm going to focus on the case where M and N are two Riemann surfaces. So we'll suppose that M and N are Riemann surfaces, and then I'm going to choose metrics on those surfaces, which have this form here, where Z and W are some local coordinates on M and N respectively. And then G and H are some positive functions. So a metric like this is what we call a conformal metric, because it is conformally equivalent to the uniformizing metric on the surface. We're just multiplying dz squared by a positive function to get a metric on M, and likewise for this surface N. All right. And then let's suppose that we have a smooth map between the two surfaces, which takes the local coordinate z to the local coordinate w. So that's the setup. And then we have the definition here, which says that f is harmonic if it satisfies this partial differential equation. And the equation looks a bit complicated, but I don't actually need to use it in the talk. The only thing that I would like you to notice about it is that it explicitly involves the metric h. So this function h appears explicitly in the differential equation, but g does not. So it doesn't depend on the precise form of the metric on the domain manifold M. Rather, it depends on the conformal structure of M. So it depends, so in other words, to make sense of this notion of a harmonic map, it is enough to just specify a Riemann surface M, and we don't have to worry what exactly is the metric that we're considering on M. And that is not true in general for harmonic maps, but if you're talking about harmonic maps between surfaces, then there's this conformal invariance property. So that is the notion of a harmonic map. And now I'd like to take a step back for just a moment and suppose that F is any smooth map between Riemann surfaces. So it could be harmonic, but it doesn't have to be. And then what you can do is look at the pullback of the metric on N. So you take that metric, you pull it back using this map F, and that will give you some tensor on the domain surface M. And then what I'd like to do is consider the 2-0 part of that tensor. So in other words, I'm looking at all terms in that expression which are multiples of dz squared. So that will give me some expression, and in fact, there's a simple calculation that gives you explicitly an expression for this function phi of z. So it's given some in terms of the derivatives of the map, and also in terms of the metric on the target. And it is a fact that if this map F is harmonic, then the resulting function is holomorphic. So in other words, you could say that the 2-0 part of the pullback metric is what is known as a holomorphic quadratic differential. So that's just a holomorphic function times dz squared. An expression of that form is a holomorphic quadratic differential. And in fact, this has a name. So this expression that we get by pulling back the metric and taking the 2-0 part is called the Hopf differential of the map. So that's how you go from a map between two surfaces to a quadratic differential. And I think it's about time to do an example. So let's suppose that our Riemann surfaces are the complex numbers and the upper half plane. And each of those is, of course, equipped with some standard metric. So on the complex numbers, you have the Euclidean metric. And on the upper half plane, you have this Poincaré metric that I wrote down earlier. So those could be our Riemann surfaces. And then I'm going to construct a map between them in the following way. So first, let's take a point in the complex numbers and take its real part. So that would give you a map from the complex numbers to the real line. And then I can embed the real line isometrically as a geodesic in the upper half plane. And if you know a bit of hyperbolic geometry, you'll know that a geodesic in the hyperbolic plane looks like a Euclidean half circle that meets the boundary at right angles. So I've illustrated that here. That's the image of this map. And then if we look at the composition, that in fact is a harmonic map. So this can be checked using the definition, but hopefully it's not too surprising, because if you remember your course on complex analysis, you probably learned that the real part of a holomorphic function is what we call a harmonic function. It has vanishing Laplacian, and so this is here I'm talking about some generalization of that concept. So that's a harmonic map between these two Riemann surfaces, and the Hopf differential can be computed, and you find that it's just a constant multiple of dz squared. So that's the sort of thing that we're talking about. But in this example, you can see that the whole complex plane is getting crushed. It's being sent to something one-dimensional. And what I would really like to consider in this talk is are harmonic maps that are diffeomorphisms between Riemann surfaces. So to talk about those, we're really going to have to rely on some existence and uniqueness results. And fortunately, due to the work of a number of people, we have this theorem here, which says if M and N are some compact Riemann surfaces, and the metric on the target has negative curvature, then any diffeomorphism is homotopic to a unique harmonic diffeomorphism. So you have existence and uniqueness of a harmonic map, and you have that it's a diffeomorphism, and such a thing exists in the homotopy class of any diffeomorphism between compact Riemann surfaces, provided the target has negative curvature. And we can apply this result in the following way. So let's suppose now that S is a compact Riemann surface. So I assume it has a complex structure. And then there's a natural map going from the Teichm&uuml space to this vector space of holomorphic quadratic differentials. And what it does is the following. So you take a point in the Teichm&uuml space, which, as I explained, is a pair consisting of a hyperbolic surface and a marking, and you map it to the Hopf differential of the unique harmonic diffeomorphism homotopic to the marking. So according to this theorem, this map psi is homotopic to some harmonic map. And I've already explained that the Hopf differential of a harmonic map is a holomorphic quadratic differential. So this is giving you some natural map from the Teichm&uuml space to this vector space. And it is a theorem proved independently by Hitchin and Wolf that this map psi, or excuse me, phi, is actually a homeomorphism. So you could think of this as saying that the map is providing a parametrization of the Teichm&uuml space by holomorphic quadratic differentials. And so this is the result that I would like to generalize in this talk. And the way I want to generalize is as follows. So the question I'd like to answer is, what happens now if we allow the Hopf differentials to have poles? So up until this point, I've considered Hopf differentials that are global holomorphic differentials on a Riemann surface. But what if we allow them to blow up at some finite set of points? What happens in that case? So I'll introduce now a framework for answering this question. I'm going to let S, and here I use this kind of bold S, I let that be a closed oriented surface, and I let P be some finite set of marked points on the surface. So probably many people are familiar with the notion of a marked bordered surface from the work of Fomin, Shapiro, Thurston. This is some case of that. So I'm just considering a closed surface with interior marked points, which you can view as punctures if you like. And then I'd like to consider the following data. So we'll consider triples where S is a compact Riemann surface, and note that I use a different font here. So this is just an ordinary S, whereas this was a bold one. So the bold S refers to something that is just a smooth surface, and then the ordinary S is referring to a Riemann surface with a complex structure. So we've got a Riemann surface. We have a quadratic differential on that Riemann surface, and here I introduce the divisor D. So I'm talking about a differential which is allowed to have poles of order at most 2 at some discrete set of points. And then I also have this map theta, which is a diffeomorphism between the two surfaces, inducing a bijection from the set of marked points to the set of poles of my differential. So this is quite similar to the notion of marking that I introduced earlier when I defined the Teichem space. So we consider triples like that, and turns out there's a nice moduli space parametrizing equivalence classes of such triples. And in fact, it's a complex manifold, and you can compute its dimension explicitly in terms of the genus of the surface and the number of marked points. So that's one space that we'll consider. That's the space of quadratic differentials. On the other hand, we can consider pairs as before. So we consider these pairs where you have a hyperbolic surface and a marking. And here we take C to be a hyperbolic surface with punctures and also totally geodesic boundary components. So here I illustrate an example of such a thing. So it's a surface, and you can see that it's got these circular boundary components. So those are the geodesic boundaries. And then we also can have punctures in the surface. And if you have a puncture, then with respect to the hyperbolic metric, it will look like a neighborhood of the puncture will look like a cusp. That's because the metrics that I consider are complete and finite area. So this is some consequence of that. All right, and so then psi is similar to what we had before. It's the marking of the surface, but now it's a map from a punctured surface into the interior of this hyperbolic surface. So it's really, it's the same sort of thing we had before. I'm just allowing my hyperbolic surfaces now to have boundary and punctures. So that's the setup, and there is a space parametrizing equivalence classes of these pairs. It in fact has the structure of an orbifold, and it'll be denoted T of SP. Okay, so now I have defined some generalization of the space of quadratic differentials and of the Teichem space. There's a bit more terminology that I would like to introduce. So if we have a map, or let me say it this way, so an automorphism of one of these punctured surfaces means a diffeomorphism of the surface that induces a bijection or a permutation of the marked points. So we allow our diffeomorphisms to permute the marked points, and two automorphisms will be considered to be isotopic if they are homotopic through automorphisms. And finally, the mapping class group is the group of isotopy classes of automorphisms of the punctured surface. So that's just very similar to the classical notion of mapping class group of a closed surface. I just modify it a little bit to allow for punctures. And so now I can state one of the main results that I proved, which says if your punctured surface has negative Euler characteristic, then there's a continuous mapping class group equivariant map going from this space of quadratic differentials to the Teichem space. And so this is a generalization of that earlier result of Hitchin and Wolf, because the way it works is you're taking a quadratic differential and you're mapping it to a point in Teichem space where the marking is a harmonic map whose Hopf differential is the given quadratic differential. So it works exactly the same way as the Hitchin-Wolf result, but now we allow our quadratic differentials to have poles of order at most 2. In fact, that can be generalized, but I won't discuss that. So that's a meromorphic version of this classical result of Hitchin and Wolf. And in fact, there is some further generalization that we can have here. So this brings me to the enhanced Teichem-Uuml space. But before I get to the definition of that, I'm going to recall some ideas related to quadratic differentials. So let's say that phi is a quadratic differential on a Riemann surface, and then near a pole of order 2 of that differential, we can write the Laurent expansion in this form. So near a pole of 2, this quadratic differential looks like some Laurent expansion with a term of the form z to the minus 2 times dz squared. So z is some local coordinate on the surface that vanishes at p. And then we can form the expression plus or minus 4 pi I times the square root of the leading coefficient in this expansion. That expression is called the residue of the quadratic differential at p. It's called the residue because you could define it in a different way. You could take the square root. You could take a square root of this quadratic differential. That would be a 1 form. And then this would literally be the residue of the 1 form. It would be the coefficient of the z to the minus 1 term. And because we're taking a square root, the thing we get is only well defined up to a sign. And so we can define then a finite cover of our moduli space of quadratic differentials, which parametrizes points in the moduli space together with a choice of sign for the residue at every pole of order 2. So in other words, to define a point in this space, I'm taking a point in the base and then choosing a definite value of this expression corresponding to each pole of order 2. So I choose a plus or a minus sign for this. That defines a branched finite cover of the space of quadratic differentials. And there is a similar cover of the version of Teichem-Uuml space that I defined. So this is what's called the enhanced Teichem-Uuml space in the literature. It's again a finite cover, and it parametrizes points in the Teichem-Uuml space together with a choice of orientation for each boundary component of the hyperbolic surface. So to illustrate, I can draw a picture like this. So this is the same hyperbolic surface that I drew before, but now I've added an orientation for each of its boundary components. So just a little arrow pointing one direction or the other around the boundary component. So that's what a point in the enhanced Teichem-Uuml space looks like. And there's a generalization of the theorem I had before, which says if your surface has negative Euler characteristic, then there is a continuous equivariant map from the space of signed quadratic differentials to the enhanced Teichem-Uuml space. And here I've introduced this extension of the mapping class group, which is obtained by forming the semi-direct product of the usual mapping class group with z mod 2 to the p. And that second factor acts in the sort of obvious way on these two spaces. So on the space of signed quadratic differentials, it acts by changing the signing at each point, at each pole of order 2. And on the enhanced Teichem-Uuml space, it acts by reversing these orientations at the boundary components. So that's some generalization. And now we were sort of led to this by asking what is a meromorphic generalization of this result of Hitchin and Wolff. And actually what we've ended up with here is something quite interesting, because this enhanced Teichem-Uuml space is known to have a cluster structure. So that's the next thing that I'd like to talk about. So as usual, when doing cluster algebras from surfaces, we define an ideal triangulation to be a triangulation of S whose vertices are the points of P. So I should say precisely the points of P. There are no additional vertices of the triangulation. And if we're given such a thing, so let's let T be an ideal triangulation of this punctured surface, then we can do the following. So if C now is a hyperbolic surface representing a point in enhanced Teichmüller space, then we can draw the edges of T as geodesics on that surface. We draw them as geodesics on the hyperbolic surface, which spiral into the boundary components in the direction given by the chosen orientations. So let me illustrate that with a picture. So on the right-hand side of this picture, you can see what I'm talking about. You see a curve here that is spiraling into a boundary component of the surface C. So that curve is meant to be an edge of this ideal triangulation. And one way to understand concretely what I'm talking about here is to lift to the universal cover of the surface. And in the universal cover, what it looks like is a geodesic that is asymptotic to a point at infinity. And that point coincides with one of the endpoints of this other geodesic, which is a lift of this boundary component. So, so when I say that you allow the geodesics to spiral into the boundaries, what I really mean is in the universal cover, you're making this geodesic be asymptotic to a certain point at infinity, which is determined by the chosen orientation of the boundary component. All right, and then if alpha is some arc of the triangulation, this process will give us a corresponding geodesic in the hyperbolic plane. And we can do that for every edge of the triangulation. We can lift all of them to the hyperbolic plane. And in this way, we see an ideal quadrilateral that contains this lifted geodesic alpha tilde as one of its diagonals. And here you see that I've labeled the vertices of this ideal quadrilateral as Z1, Z2, Z3, Z4. And the thing that you always want to do whenever you have 4 distinct points in RP1 is take the cross ratio. So let's do that. You can define the cross ratio X alpha in this way. And that gives you some collection of real numbers associated to the edges of your triangulation. And in fact, for any ideal triangulation, these numbers X alpha provide a homeomorphism from enhanced Teichmüller space to the product of n copies of the positive real numbers, where n is the number of arcs in the triangulation. So in other words, these numbers are providing coordinates on the enhanced Teichmüller space. And these coordinates, moreover, have some interesting cluster theoretic properties. So they transform by cluster Poisson transformations when we change the triangulation. And here I've just here I show you the transformation rule when you do a flip of the triangulation. So you can see that the coordinates change by this usual formula for transforming cluster X coordinates. So you can see that there's some interesting cluster structure that emerges when you try to generalize this classical result of Hitchin and Wolff by allowing your quadratic differentials to be meromorphic rather than holomorphic. And there's much more that I could say, of course, about the relationship between the cluster structure on Teichmüller space and quadratic differentials. But this is all the time I have, so thank you very much for your attention.
Are there questions for Dylan? Looks like there's one in the room.
Yeah, in the back, in the very back.
Okay.
Yep.
So thank you for the lovely talk.
Thank you.
I have a number of things that I'm wondering about, but I don't know. I probably shouldn't try to ask all of my questions. Is there any way to change the, can you change the sign associated to a cluster and, or sorry, associated to a puncture? And does that give you, is that a thing you can do?
Change the sign associated to a, yeah,
Like,
yeah,
can you relate
so that,
the Teichem-Uuml spaces where you've changed the signs?
yeah, so that would define some automorphism of the enhanced Teichem-Uuml space by changing the sign. And that's sort of a natural thing to do. Remember that the map that I defined is equivariant for this group action. So that's sort of compatible with changing the sign associated to the pole of the differential.
Okay.
Maybe we could discuss it further, because
Right.
I'd kind of like to know why you were wondering about that, but
Okay.
it's I mean, it's related to things in cluster theory, like you know, there's this Donaldson-Thomas transformation, which is a composition of factors, one of which is, I think, changing the sign.
Yeah. I guess I was vaguely remembering things from like Bridgeland Smith, and like there's some other, I don't know, there's some...
yeah. So actually, let me comment on that. So in that paper, they were giving an alternative approach to the notion of a tag triangulation. So the tag triangulation is this concept developed by Fomin, Shapiro, Thurston for describing all of the clusters in the cluster algebra. So not all of them arise from ordinary triangulations. You also have what are called tag triangulations. And one way of thinking about a tag triangulation would be an ordinary triangulation together with a sign at each puncture. And then these are subject to some equivalence relation. And this operation of changing the sign is called a pop. It has some importance in the theory.
Right, thanks.
Mhm.
And since we're looking at the slide, sorry, this will be my last question, and I'll let other people ask.
It's okay.
But this psi and the psi that you had earlier, are they in the Hitchin-Wolf result, their homeomorphisms? Are they here as well?
Well, yeah, that's right. In that result, it's a homeomorphism. But here it cannot be, because I've defined my spaces a little bit differently. So here, rather than fixing a complex structure, I'm allowing the complex structure of the Riemann surface to vary. So if I fixed a complex structure, then I would get like I could formulate a result where you do get a homeomorphism. But here, because I allow the complex structure to vary, this space on the left, this space of differentials, is actually twice the dimension of the one on the right.
Oh, okay, gotcha. Thank you.
Yeah.
Any more questions in the room?
Any questions from the Zoom meeting? I don't see anything in the chat.
No room questions either.
Okay, well, let's thank Dylan again.
Okay, thanks very much.
That concludes our session for today. I think that those who are lucky enough to be in the meeting are going to a formal dinner later today, and the rest of us will just have to make do with emojis of a formal dinner or something.